Hi everyone and welcome to this my video on solving quadratic equations over the complex numbers plane. Oh my goodness. Do you remember doing this in year 10 and 11 and maybe 9 and you're going, oh, no quadratic. I know, same idea, but now we're going to do it with complex numbers. Like, it couldn't get any more exciting, could it? Well, possibly. My name's Darren from Maths Guru. Thank you very much for joining me in this video, part of the Specialist Maths series here in Australia. But it doesn't really matter because this stuff is universal. Well, maybe not universal, but it's certainly global, and hopefully you're going to enjoy it. If you're new and can subscribe, that will mean the world to me. It just lets me know that you actually watched the video, because otherwise I don't tend to get any feedback other than things thrown at me in public. But that's a whole new discussion that we might go into. And learning objectives, I thought so too. We're going to understand how to factorize quadratics over the complex plane, solve quadratic equations over the complex plane, and know how to use your CAS to assist with the following. All right, now we have done a lot so far in previous videos. And again, all of these videos are available from mathsguru.com. Absolutely free to sign up. So hopefully it'll provide you stuff over there that you need. Right, what do we have looked at so far? What a complex number is and how it's represented. Yep. How to find the length, modulus and conjugate. Yep. Divide complex numbers, put them in polar form and perform basic operations. Right now, obviously, as the chapter has gone on, we are going to get more and more complicated. And thank you so much to Cambridge for allowing me to use your examples. You guys absolutely rock. Cannot thank you enough for the permission to do that. Right, let's see. Now, factorization, what is it? Now, remember from past years of, trauma and whatever else, there we go, there's a quadratic, and what can we do? Well, we can rewrite it the other way around. A lot of people go, why would you do that? Because then it makes obvious sense that y equals 0 is where you are trying to then solve or, find the crossing points for. Because ultimately, with quadratics, you're going to realize that it's going to have no crossing points, one crossing point, i.e. a touching point, or two crossing points. Yes, and we have so much theory that we can use. You've got the T method, you've got the cross method, so many ways to do it. And with that example there, when I take this quadratic and I factorize it and then use the null factor law to solve, I get that x equals 1 and x equals minus 2, which we know point to the crossing point. But we came to a point where actually there were situations where quadratics didn't have any crossing points, in which case they had what we call no real solutions. And I think many teachers out there would have gone, well, there's no real solutions. And what we're trying to say there is, well, there's not real solutions, but there are, in fact, complex solutions. So whenever you end up with the idea of the discriminant, which is b squared minus 4ac, whenever that was negative, we used to tell you, oh, no, it can't be solved. Oh, dear, it can't be solved. Well, guess what? Now it can. And that's exactly what we're going to be doing. Okay. One of the beautiful tricks of this is, and it again is an idea that we've used in a previous video, is that I squared is equal to -1. We like that. Now, if we've got the idea, if we ended up with a quadratic in the terms of, say, z squared plus a squared, where a could be a constant, for example, well, at this moment in time, we can't use anything. Remember, we taught you DOPS before that basically said that when you had something like x squared minus a squared, you were good. As long as that minus sign is there, you could do x minus a, x plus a, and life was really, really good. But we don't have that here, do we? We've got a plus. Hold on a moment. What if I use the idea that z squared minus a squared I squared was exactly the same thing? Now, again, let's unpack that. I squared is -1. -1 times minus gives me the positive. So actually, these things here are exactly the same. Well, I can write that then as z squared minus ai all squared, and we're back to DOPS. So therefore, that factorized would be z minus ai and z plus ai, which, if we made that equal to 0, we could then theoretically go ahead and solve. Okay, so basically the theory here, to boil it down, is wherever you see a z squared plus some sort of an a squared, we can do something with it. A couple of examples. Oh, look at that. Z squared plus 16. Well, I'm going to write that as z squared minus 16i squared, which is z squared minus 4i all squared. Now, again, careful there because that 16 has to square root to become the 4, all right? So they are exactly the same, and therefore we can say that z squared plus 16 becomes equal to z plus 4i and z minus 4i. Well, What about this one here? Again, no different from the tricks we actually employed in previous years. Whenever that's 2z squared, what I'm going to do is take 2 out of my factor. So it's going to be 2 in brackets z squared plus 3. My voice is going because of the number of videos I've recorded. Now that's going to become 2. I'm going to do some open brackets like that for a moment. Z squared minus 3i squared. 2 lots of z squared minus root 3i all squared. And therefore we get 2 lots of z minus, I'm going to do I root 3. And, oh, I'd write an x, see? And z plus I root 3. All right, and there we go. We have that factorized. Now, again, the only reason I'm writing the I beforehand is in previous sort of sections of this course, we put the I there so that we didn't get confused, because it is a very, it's unlikely we would get that wrong. Whereas if we did this, that looks like that, and then we have all sorts of problems if we end up with a transcription error. So probably best not to worry about that for the moment. All right, more examples. Factorize the following. Well, there's so many different ways of factorizing. If I had that one there, I have 2 ways of doing it. Quadratic equation, that works. No, not quadratic equation, quadratic formula, or completing the square. So for the examples for the moment, I'm going to have a look at completing the square and see what happens. Now, I know that when I complete the square, so long as this is a monic, and at the moment it is a monic because there's just a 1 in front of that z squared, I'm going to do z, all right, plus a half, close brackets, all squared, right? Now, why have I got that? Because at this moment in time, if you remember, for the way I do it, we half the coefficient and put it inside. Now, when I multiply that out, I'm going to get plus a quarter. I don't want plus a quarter. So I've got basically to take away that quarter and add on the 3 that was already there. Okay, so half squared gives me the quarter, get rid of it, and then just basically add on the 3 there. All right, okay, so going to my next line, I'm going to get z plus a half all squared. That's going to be plus 11 on 4. Oh, I can't do anything with that. Yes, I can. I can make that a minus and just make that I. Yay! Right, see what we've got there? In fact, no, make that an I squared. Sorry. Right, what do we do now? Well, I'm not going to get tricked. I always write this line, so that's z plus a half all squared minus root 11 onto I all squared. So therefore, my factors are going to be z plus a half plus root 11 onto I, and z plus a half minus root 11 onto I. Ka-ching. All right, so there we go. That's completing the square for that one. Okay, moving on to this example. Can I still complete the square? I should Coco, but I'm just going to take 2 outside a set of brackets, which is going to give me z squared minus a half of z plus a half. That's going to give me 2 lots of, right, z minus a quarter all squared. Let's make that bigger bracket, z minus a quarter. Minus a quarter squared is 1 on 16. I need to take away that 1 on 16 and add on my half that I already had there. All right, so again, when I do minus 1 on 4 squared, I get minus 1 on 16. I have to get rid of that and then add on my half to do that. So that's giving me 2 lots of square brackets. Again, z minus a quarter all squared. Right, minus 16 plus a half, that's going to be 7 on 16. So plus 7 on 16. Now, that plus I need to be a minus, so I'm going to make that I squared, which means I get therefore 2 lots of z minus a quarter all squared minus root 7 I on 4 all squared. Okay, so therefore my factors now become 2 z minus 1 quarter plus root 7i on 4 and z minus 1 quarter minus root 7i on 4. And there we go. Those are my 2 solutions there. What about this one? Does that make life any more disgusting? Yes, it looks disgusting, but we can do exactly the same thing here. So we take out a 2 outside of my brackets, and I'm going to get z squared minus 3 minus iz plus 2 minus 3 on 2i. Oof. Okay, so completing the square, I get 2 lots of z minus 3 minus I all on 2, all squared. Right, 3 minus I on 2 all squared is going to give me plus, I want to minus from that, 3 minus I all squared on 4. And recombining this last fraction once again, should have just left it, was 4 minus 3i all on 2. All right, now actually what I'm going to do is, because I noticed I've got a denominator of 4 there, I'm going to make that 4 as well, which means I'm basically going to have to double all of those as well. So actually I'm just going to cross that forward to make that 4. That's going to become 8, and that's going to become 6. All right, where do we go now? So 2 lots of z minus 3 minus I all over 2 all squared. Right, so 3 minus I all squared is going to give me 9 minus 6i plus I squared. Well, I squared is minus 1. So 9 minus 1 gives me 8 minus 6i. So that's going to be minus 8 minus 6i on 4 plus 8 minus 6i on 4. And guess what? Those two cancel. And so in which case, my completed square gives me 2 lots of z minus 3 minus I squared on 2. There we go. And so I have factorized that quite nicely, I think. Z minus 3 minus I, yep, all on 2. Now, we can use the quadratic formula. It might make life easier in some examples rather than others. So I'm not going to do all 4 of these because we could literally be here all day. But you can certainly test it if you want to. Now, the quadratic formula says x is equal to minus b plus or minus the square root of b squared minus 4ac all on 2a. So in this situation, my solutions are going to be z is equal to minus 1, because that's b, plus or minus the square root of b squared, which is 1, minus 4 times 1 times 3, all divided by 2 times a, which is 2. So z becomes equal to minus 1 plus or minus the square root of minus 12, that's minus 11, all on 2. So z becomes equal to minus 1 plus or minus the root of minus 11 is going to be I over root 11 on 2. So therefore, if we were going to solve each of these, and that's slightly different in terms of solving, I therefore say that, well, basically that z is equal to minus 1 plus root 11 I on 2, or z is equal to minus 1 minus root 11i all on 2. Now, as I say, there are lots of other examples here that we could do. I'm really not going to do it. Obviously, the trick with this one here is to rewrite it in the form of z squared minus 2z plus 5 equals 0 to then go on and do the quadratic formula. But let's skip all these examples for now. Now, again, your CAS can do the hard work for you by simply using the idea of C-solve. All right, so what is that? Complex solve, put in your equation, and lo and behold, out comes your solutions. Right, let's have a look at a couple of VCAA questions. Of the number of distinct roots of that equation, where z is equal to complex is, distinct roots. How on earth would I find the distinct roots? Well, it just so happens you can fire up your CAS calculator. Why? Because by putting in C-solve and that equation, I am counting off that I've got 1, 2, 3, 4, 5 distinct roots. My calculator has solved my problem by making D my correct answer. What about this one here? The principal arguments of the solution of the equation z squared equals 1 plus I are. Now, believe it or not, this is actually quite a challenging question. And there's a little bit before the theory that actually deals with it. But is it? Now, z squared equals 1 plus I. We don't quite know how to solve that, but I do. I know that z is equal to r cis theta. So z squared, if you remember, is r squared cis 2 theta. Okay. So we know then that that z squared can be written as r squared cis 2 theta. Sorry about my voice, it's going because I've recorded a lot today. Now we know that we can write 1 plus I in cis format as well, because 1 plus I is going to be, well, 1 squared is 1, the coefficient in front of the I is 1, well, that's going to give me root 2, so that's going to give me root 2, cis, and what I need to do is find my principal argument of that, and it's actually pi on 4. So there we go, that's pi on 4. Now, we know because of the equal sign that what's on the left-hand side and what's on the right-hand side must be exactly the same. So therefore, we know that r squared is equal to root 2. So r squared basically becomes 2 to the half, or r becomes equal to 2 to the quarter. Now, interestingly, it didn't ask me for that question, but it doesn't hurt. Now, here's the trick. Remember, this is my principal argument, but there's not just that one solution. Remember, I can get other solutions to this by adding on a factor of 2k pi, all right? Or more importantly, 2 pi. So let's see what happens here. We now know then, therefore, that 2 theta must equal pi on 4. So 2 theta is equal to pi on 4. That's certainly one of my solutions, but I have to add on 2 pi to that as well, all right? So I have to keep adding on actually that's 2k pi. 2k pi, where k is in the number, you know, or whatever you want it to be. So dividing that then, we get theta is equal to pi on 8 plus some multiplier, he says, come on, k pi. Now, I don't really like using the letter k. Maybe I should have used n there, because n can be 0, 1, 2, 3. That k seems to remind me of that -1, 0, and 1 business. But my theta values are now going to be pi on 8 plus, or in fact minus, values of pi. So certainly one of my solutions is going to be pi on 8. That's good to know. Well, pi on 8 plus pi gives me, what is that, 8? 9 pi on 8. Oh, that's not particularly useful because that's not a principal argument. Aha, but I can take away 2 pi from that, because that will then give me an answer. So take away 16 on 8, 16 pi on 8 from that. 9 minus 16 is going to give me 7. So also 7 minus 7 pi on 8 is going to give me my solution. Have I got one of those? Pi on 8 and minus 7 pi on 8? Pi on 8 and minus 7 pi on 8? Yep. So I think C is going to be my correct answer. Now again, that's a little before where we needed it to be, but it seems to work. And I'm done. Right. Did we understand how to factorize quadratics over the complex plane? Yeah, pretty much what we did before. But using the idea of dots, or the sort of theory we'd used before. Solve quadratic equations over complex? Yep. Understand how to use the CAS? Yes. And we've done some VCAA questions as well. Result. Thank you very much for watching. Hopefully it's been useful. If it has, do me the honor, please, of liking and subscribing to my YouTube channel. Again, it just lets me know that people have been watching. Hopefully you will join me with more videos in this series. If so, I'll see you then. If not, please take care and stay safe. Bye-bye.